Hey, everybody. Welcome back to Calculus 3. This is 11.3. We're looking at the dot product. This is a form of vector multiplication where we multiply two vectors together. In this section, we're going to look at that and projections and talk about what dot product is. We've got a few sections that we'll be covering over several videos for 11.3. So let's start off with two vectors in 3 dimensions, u and v. And the dot product is, we use a dot, u dot v is you take each of the components individually and you multiply them together and take the sum. So the x components are u1 and v1, we multiply them. Y is u2 and v2, we multiply them. And u3 and v3, and we multiply them. Add them up, and that's the dot product. It produces a scalar. So there is no vector when we do the dot product. Okay, it produces a result. We'll see what that means geographically in a little bit, not graphically. Some properties of the dot product. It is commutative. If you go through and switch the order of u and v and multiply them together, you can go through all these steps and practice them out, see what it looks like. So u dot v is the same as v dot u. The dot product is distributive. U dot v plus w is u dot v plus u dot w. When we distribute a scalar, we only distribute to one of them. So if we're doing k times the u dot v quantity, we either do it times u or times k, ku dot v or u dot kv. If you tried to put it on both, you'd notice you'd get k squared, and that's not the same value. If you do v dot v, you're going to get, notice we'd have v1, v1, so that's v1 squared. v2, v2 is v2 squared. v3, v3 is v3 squared. That would be, if we have the square root sign, the norm or the magnitude of the vector v. So, but since we don't have the square root sign, it's that value squared. So v dot v is the norm squared. And the zero vector times any vector produces 0. Some basic stuff. Properties that you should know. They're very similar. In fact, you'll find that a lot of this stuff applies, what you learn from the real numbers applies here. If u and v share initial points, like they start at the same point, tail to tail, the angle between them, theta, where theta is between 0 and pi, are related to the dot product by the law of cosines. So if you don't remember the law of cosines, I drew the picture here. If we've got A, B, and C, and theta is between A and B, the law of cosines formula is c squared equals a squared plus b squared minus 2ab cosine of theta. Now, when we shift that to 3 dimensions, if I'm looking at the angle right there, u and v, there's the right one's the u vector, there's the v vector. The lengths of them are u, the norm of u, the norm of v. And this over here is u minus v. Remember, we do the endpoint minus the starting point. So the norm of u minus v squared, just plugging stuff in from the law of cosines. The norms of u squared plus the norm of v squared minus 2 times the norm of u times the norm of v times the cosine of the angle between. Well, the red, the one on the left, if we write that out, that's u1 minus v1 squared plus u2 minus v2 squared. And you multiply that all out, we get this right here, u1 squared minus 2u1 v1 plus v2 squared. That's the first parentheses. And then u2 squared minus 2u2 v2 plus v2 squared. That algebra stuff has come back and it's nasty with all the subscripts and superscripts and stuff like that. But it's there. If I look at the right half side, I've got the norm of u squared is u1 squared plus u2 squared. I've got the norm of v squared is v1 squared plus v2 squared. And then I've got minus 2 U1 V1 plus U2 V2. I'm sorry. That's just me regrouping this line right here. Sorry, that doesn't, what I just said doesn't make sense. But it is similar. If we do that right side, so I got U1, U2, that's here. That should say V1. Look at that mistake. V1 squared, V2 squared is right there. And then minus 2U1 V1 minus 2U2 V2. I factored out the minus 2. If we break out the right side, what I've done here is I didn't actually break anything out. I rewrote this line right here. This is the norm of U squared. This is the norm of V squared. And this is U dot V. So I've rewritten the left side right here. U squared, norm of U squared plus norm of V squared minus 2U dot V. We still have the right-hand side. You'll notice we have U squared plus V squared, the norms of on both sides. They are real numbers, so we subtract them from both sides and they cancel out. And we're left with minus 2U dot V is the same as minus 2 norm of U, norm of V, cosine theta. We're almost done. Divide by -2, we see U dot V is the same as the norm of U, norm of V, cosine theta. Or we can write it in terms of cosine theta rather than the dot product. Cosine theta is U dot V divided by the norms of both of them. Okay. It's kind of neat. So let's take a look at an example of that. I've got the vector U and the vector V, 2, 2, and -3, 1. We can graph them and we can see the angle between them. And when we work on finding the angle, or the angle, if we want to find the angle, we need the norm of U and the norm of V. So the norm of U is 2 squared plus 2 squared, then take the square root, square root of 8. V, same process. We're doing the distance formula. We get square root of 10. If we do U dot V, we've got 2 times -3 plus 2 times -1, we get -8. So cosine theta being that U dot V over magnitude of U and magnitude of V, I've got -8 over root 8 of 10, which is -8 over the square root of 80. If I do cosine inverse, we'll see that it's approximately 153.4 degrees or 2.68 radians. Okay. That's it for this section. Peace. Ooh, bump the camera.